All right, so we'll go ahead and get started with the practice exam one. Oh, one more thing. I just sent an email to everybody. Some of you who check your email on your phone probably got the message already. So I'll just go ahead and talk about that a little bit. Nope, this is not 300. So I just sent out this message to the entire class, and it's loading it. Did you guys notice that this morning the network went down for like periods of 10 minutes or so? It was I think it occurred twice this morning. Okay, so it wasn't just me. All right, the IT people did not reply to me when I mentioned that. It's like, tech, go away, go away. If tech goes away, the problem will go away too, because it doesn't get reported. Anyway, I have a new virtual machine, and this one is just the disk image. In other words, this is not a whole package. It's really just the QCOW2 file. But in this case, it's already an installed version of Debian, and that's all you need. It's just the virtual disk file. Uncompress it is a zip file. You can uncompress it using Windows. And then in your startup script, you have to make a few changes. The changes I have already described here. You don't need deblive.iso anymore because it's already installed. You do not need the live distribution anymore. So if you use it this way, you might be able to save some space on your flash drive. You have to take out -boot D because without -cd-rom, there's no D drive, there's no CD-ROM drive to boot from. Change your -HDA to -HDA HD-P453.QCOW2 just to redirect the file name to the proper QCOW2 file. And in this case, you probably can even shrink the amount of RAM to 256 megabytes. So for those of you who are trying to run the virtual machine on an older machine that only has like 1 gig of RAM or so, this one will run more efficiently too. The rest you can keep. You can basically keep all the -net and all the other options. So whatever you have elsewhere, in your startup script, you can just keep it. This one starts up significantly faster, even with the same hardware. So I would, if you have been bogged down because the other one starts up too slowly, and even in text mode, this one will make a big difference. You will see the difference. The file itself, I think, is about 300 megabytes. It expands to about 500 megabytes. I tried to shrink it down, but I couldn't really quite, shrink the distribution down, given that I didn't really have too much time to play with this. But this will work. I tested all the tools that I use in the class. They're all there. It can assemble programs. It can compile programs in C. So it may be even sufficient. Well, it's not going to be sufficient for your C++ classes because I did not install G++. But once you download this, you can actually go ahead and use aptitude or apt-get to install G++ as well. So if you want to use the same distribution for your other classes, you can actually do it. The virtual disk has a maximum size of 2 gigabytes, of which about 500 megabytes are used. So you still have a lot of space left if you want to install additional tools. It does not come with a GUI. In other words, there's no Firefox, there's no Google Chrome. If you want to use this alternative, you will have to use PuTTY to putty in, to edit and run your programs, and also you use WinSCP to transfer the files in and out of the virtual machine, which is not a big deal. It's but the efficiency gain is, I think, is well worth it. All right, so that's an alternative. You don't have to do it this way, but if you want to try this out, feel free to try it out. So now we are moving on to the practice exam. Practice exam 1, which is right here. Last year I was doing this on a computer. So as a result, I was able to. Well, the whole class took the test on a computer. So that's why people were able to assemble the program and actually try to debug the programs. That turned out to be both a good thing and a bad thing, because I know some people in this class are thinking, well, I wish I could take this test, with a computer. The problem with a computer is, when people do it with a computer, they really want to fix everything to make it work 100%. And a lot of times, they miss one little thing, the program keeps on, not working, and they just waste the whole time, trying to fix that one little thing and not move on to the next question to get, some score partial credit for the next question. When you do it on paper, I cannot expect you to be able to fix everything because you don't have the assembler to help you, you don't have GDB to help you, you don't have the tools. So you basically will just have to rely on your analytical skills to look at the program, find out what the problems can be, and then fix the program or make it work. So that means, the scoring standard will be a little bit different. I cannot expect people to get it to work. I will have to see how many of the problems that you can solve, or how much of a solution you can come up with in the case of a on-paper exam. So an on-paper exam actually may not be so bad, because of that. All right, so let's go ahead and I'm going to download this again, but this time into the folder, into today's folder. So if someone reminds me to upload it at the end of today, it will actually contain the answers as well. All right, so let's go here, double check how much space I have. We got 3.6 gigabytes, so we should have enough space today. All right, so the first thing I do is to untar this. Obviously, this really doesn't apply to you anymore. All right. So we go to exam 1, and then we take a look at the questions. I give multiple versions of these questions, so that neighbors, sitting next to each other may or may not get the same version of the question. So for the most part, I will only take a look at one of these questions for each one, and we'll take a look at Q18 PDF. Does it look okay to you, or do you want a different viewer? Yeah, too big. Can't see the whole thing. Is that okay? Sort of? Okay.
It's a little small.
A little small? Yeah. Let's see if I have a text version of the file. Yeah, I do. Okay, we can use a text version of the file. Okay. So is that better?
Yeah.
Okay. So what we're going to do is to replace the above instruction, meaning this one here. And if I turn on line numbers, we can actually refer to the line number. So the question is, replace line 21 with instructions that will copy the same memory content to register AL based on the values of the memory content and the values of EBX and EAX, because you can see EBX and EAX are a part of that operand when the instruction executes. This means that my test script will alter the values of EAX and EBX prior to the execution of this code, which means this line here. And your code has to perform exactly the same memory copy operation as this instruction here. In other words, I'm looking for ways to implement exactly the same as this instruction, but not using the complicated addressing mode here. So the restriction, is in the next paragraph. You have the following constraints, your restrictions. Use only the add and the move instructions. You have to figure out the width of the instructions. You can only use immediate, register, and indirect operands. Okay. You can use EAX, ECX, CX, CH, CL as temporary registers. As a reminder, the effective address of a general operand is this mess here. We talked about that in the class already. Assuming the format looks like this, which is the format here. Okay, so that's your question. The question is, I only let you use the move and the add instruction, and you can choose the width of the operations. You can use B for byte, W for 16-bit, and L for 32-bit. You can only use the real restriction here is not so much the instructions, because we have only talked about 3 instructions so far, okay, or 2 that applies to the exam. The subtraction and the compare instructions will not be in your exam because we have just started to talk about it. So for the most part, we only have 2 instructions that can be in the test. One is the move instruction, which is the same as copy, and the other one is the add instruction. And you are allowed to use either one. The real constraint here is you can only use immediate, register, and indirect operands in order to implement that one single line on line 21. Okay. Are there any questions at this point? Right after the exam last year, a lot of people came up to me and said, this question is not fair. We have not talked about this. We don't have enough tools to do it. Well, actually we do. Okay, let's take a look at this part here first. Okay, the highlighted portion. The effective address is the displacement, which is the number outside of the parentheses, plus b, which is the value of the base register, plus I times s. I is the index register, and s is the scale, which in this case is a constant of 4. Okay? In other words, instead of using that particular addressing mode, which is called the based, scaled, indexed operand, you have to do the same thing, but only using move and add, and only using the 3 operands that you are allowed to use. I don't think we have a problem with the adding part. The real problem is, how are we going to do the multiply? After all, we have I times s. You can add twice, exactly, because at once, if you add a register to itself, you're doubling, and if you do the same thing again, it is quadrupling. It's the same as multiplying by 4. So we have all the tools to do this. Let's go ahead, and I'll just do it in place and save the file, so this way you can have the solution when you download the whole folder here. Okay. And I think last year they had to do it on paper too, because otherwise there wouldn't be like a whole bunch of underscores here, as a place for people to write down the answers. So let's go ahead and take a look at the answer. I want to be able to look at this and also work on it at the same time, and VI lets me do it because I can split. Cool.
Oh, that's cool. I like this more and more every day.
It has a lot of neat little tricks. You can actually split vertically too if you wanted to. I think it's V-split or some other command. But horizontal split works better because I can still refer to the instructions in this case. All right, so let's go ahead, and the instruction says very clearly you can use ECX as a temporary register. In other words, you can basically say the value inside ECX does not need to be saved, and I can use ECX for some particular purpose. So what I'm going to do is I will use ECX as a register to store the address of the operand itself. In other words, I'm going to use it as my temporary register to compute the address. Okay? Now let's think about it. Out of this entire equation, where should I start? What should I start? How should I start initializing ECX in this case? If I want ECX to contain the effective address of this original operand, which is on line 21 here, where should I start?
What EA is for the current value, I guess.
I will start with EAX, right? We want to perform the multiplication first. The other ones are just add instructions, and I can do it anytime I want to. But the multiplication has to be done first. Okay? So we'll go ahead and do the multiplication first. The multiplication goes like this. Okay, the first thing is I have to copy EAX to ECX. Okay? So now ECX, okay, I'll just use comment here, and I'll say ECX is EAX at this point. Is that okay? That's not surprising. The next instruction is an add-L instruction. I'm adding ECX to ECX. What does that do? Well, it's basically the same thing as this in C, which is the same thing as ECX equals ECX times 2. Are we doing okay so far? Now, the value of ECX right now is the same as EAX, so that's basically saying ECX ends up with a value of 2 times EAX. I'm not going to change the value of EAX, so EAX has a fixed value, and so does an EAX. Okay. What if I do this again? I add ECX to ECX again.
double it again.
We're doubling it again. So in C, this is what it does. But what is it equivalent to? What is the value of ECX at this point? In
4 EAX?
4 times EAX. Because we doubled it twice. And that's why it is now 4 times EAX. Now what is that product of any consequence in this particular case? That's my scale times my index register. So that's why it is important. I'm done with I times S already. I just have to finish up the rest now. Okay. So I'll just put a comment here, and I'll say I times S is now computed and stored in ECX. Are we doing okay so far? Now the rest is really a lot easier, because the rest is really just adding the base register and also the displacement. The order really does not matter in this case because it's addition. So you have the rule of, it's the commutative rule that allows you to change the order of the addition. Yep.
You said that you were going to put this up online, right?
Yep.
Okay.
So at the end of the class, I cannot do it over there at the lab because I cannot. There's no way for me to access my persistent drive because those machines only runs Windows and they won't let me reboot to Linux. So earliest I can do it is when I get home.
Okay.
So if you kindly send me an email, I will remember to do it.
Okay.
Don't just say tech, do it. Do what?
Can I say it as a joke and that'd be nice?
Yeah, just a kind reminder, like tech, could you upload the folder of today's folder, to Moodle. That's fine. All right, so let's go ahead and do this part. The rest is actually quite easy until the very end. Then it gets a little bit tricky, but not too tricky. Okay, so I'm just going to finish, let's say the base register. The base register is EBX in this case. So I'm going to add EBX to ECX. So that's the same as ECX plus equal EBX, which means ECX at this point is going to be the same as 4 times EAX plus EBX. Is that okay? Okay. And then we can add the constant to it. The constant is really just L1. Now, this is $L1 and not L1 by itself. Because L1 by itself is what addressing mode?
Direct?
It's a direct operand, and it is not allowed. And that would also be the wrong thing to do as well. So you do have to make sure that you use the $ in this case, because I really want the value of L1, but not the value of the byte at location L1. Okay, so those two are very different things. So I'm going to add it to ECX. So at this point, it is the same as saying ECX plus equal to L1, which is a constant, it's a number. So it's the same. So right now, ECX has 4 times EAX plus EBX plus L1. I think ECX has the address at this point. We have just added everything. Okay, so I'll just put a comment here. D plus B plus I times S is stored in ECX at this point. I only need one more instruction to do it. I need a move byte instruction in this case, indirect ECX to the destination, which is AL. That finishes the whole operation. Are we doing okay so far with this little translation? Yep.
I didn't see in the file where the label L1 was defined.
Yep, it's right there.
Okay. And then that is the memory location of the instruction that precedes it.
After, not precedes.
Proceeds.
Yep, after that. All right. Yep. Oh, I think you had a second question. Go ahead.
Just really quickly, what are those percent on the right?
The percent on the right?
On the black stripes.
On the what?
On these two black stripes.
The two.
40%, 75%. What is it?
Oh, that's what is the position of this window relative to the size of the file? Okay. Yep. Go ahead.
So you said you can use ECX, but do we have to use ECX?
If you don't use ECX, you will have to destroy one of the other registers. Because during the computation of the address, you have to store that into a register.
Right, but since you don't say not to do that, is it okay?
I think in most cases, because the original instruction does not destroy the values of EAX and EBX, so I want to emulate that from the original instruction. So I have to designate a register that is useless at this point. I can use it as a scratch pad, basically. Okay. Any other questions? No question like, why do we want to do this? Why is this even useful? Oh man, I was about to answer that question.
Why is that useful?
All right, very good. Good job. It's because, okay, the main reason why we have to do this is because this is very handy, okay? Especially later on in this class, you will see applications where, hey, I can do it with one single operand and be done with the operation that I want to specify. Unfortunately, this is a cisp feature. It is a complex instruction set computer feature, which is lacking in the RISC processors. The RISC processors have exactly the same constraints that is described in the question itself. Okay? The constraints of only having immediate register and indirect operands, that's exactly the constraint when you're dealing with an ARM processor, a MIPS processor, or Spark processor. Those are all prime examples of RISC type architecture. So that means, even though it would be nice to use a single operand when you have that option in a cisp processor, when you're dealing with a RISC processor, it really has to translate that into these instructions. Okay? And that's why this particular exercise is actually significant. Yep.
I know I used to know, but I forgot now. What do the parentheses do on the move B on ECX?
The parentheses surrounding ECX turns it into a indirect operand.
Which is what exactly?
Aha. Okay.
Yeah,
So I can see some studying coming in the next in the following week. An indirect operand means the value of the operand, in this case, is the byte at the location, at the memory location specified by the register ECX.
All right.
Yep. All right.
Can
When
say
you
it
first,
again?
sorry,
Can you say it again?
the value of the operand, which is an 8-bit value, you can
Right.
see it's a move byte instruction, so that means we are only dealing with 8 bits. The value of the operand is the value of the byte at the location specified by ECX. We take the content or the value of ECX and use it as an address. Go to that location in memory, grab that 8 bits, and that becomes my first operand. And that's what's going to be copied to AL in this case.
So it looks for the address. So yeah, that's not the value of the 8 bits. It's the address that points to. Is what you're saying?
ECX is basically acting as a pointer,
Okay.
and the parentheses is kind of like a dereference.
Right.
Okay.
If you didn't have the parentheses, then you had to have a file error, yeah?
It will have an assembly error, or a warning at least, because then you'll be specifying a move byte instruction, but the operand itself is 32-bit. And the assembler does, I think it gives you a warning. It will quote-unquote cast it to a different width, but I cannot remember which one takes precedence, whether the register or the instruction takes precedence. I cannot remember.
If you wanted to do that instruction, you would just refer to the lower part of the register, right? Using I forget exactly the letters, but ECX has a 32-bit, and then you can refer to EBX and then EAX or something like that.
I think you're referring to AL and AH.
Yeah, that thing.
Yeah, but that's a totally different type of operation. That would be a register to register copy. This is a memory to register copy.
Right.
Okay. Yep.
So just to make sure that I'm understanding the instructions correctly, the idea is we're supposed to recreate the value in AL after line 21.
We are supposed to implement a sequence of instructions that has the same effect as the one single instruction on line 21.
So we don't need to bother with the 2 move L's at the beginning, or
The 2 move L instruction. We're only trying to re-implement line 21. So whatever is before line 21 is not important.
so just the value of AL
we are taking this instruction completely out of its context and just say, in general, if I see an instruction like this without knowing what the instructions are before that one, how can we replace this one single instruction on line 21 by a sequence of instructions, given that I know that ECX may be trashed as a result?
It would be like writing a function in C to do what happens on.
It's kind of like more like a macro in this case. I'm just expanding one instruction into multiple instructions.
Okay, I think I got it.
Okay, very good. Yep.
How many questions are going to be on the exam? Is this a single question or?
No, there'll be multiple questions. This is the first one. Are there any questions about the first question? Yep.
For the indirect operand, can it work on like label or constant?
No, only registers. You can only put a register inside the parentheses. Yep. All right. So the first question is good. We're okay with the first instruction. The first question. We can move on to the second one. So from now on, I'll just look at the question itself, the file, the source file. Okay. So question number 2. When the program stops at the checkpoint, which is a label, EVX should have a value of 566E7F. I know how much you guys like this kind of questions. Fill in the question marks to make this work. Your changes are limited to replacing the question mark with values. You cannot change the mode of the operand. So if it was an immediate operand, it has to stay as an immediate operand. Keep in mind that the x86 processor is a little endian processor. This means the least significant byte is stored at the lowest address. Note that this question is has non-unique solutions, and lots of them. So you just have to find one that works. Okay. Now, does that remind you of a certain homework assignment?
It's almost like we just did.
So it's a miniature homework assignment. Okay, let's take a look at the question marks. There are 3 question marks here. One question mark initializes EVX, which is going to be used down here. But we also have another instruction here that can change the least significant byte of BL. That should ring a bell. And the third question mark is here, which is the offset, based on this is a based indexed addressing mode. Okay, and this one is fixed. That one is fixed. All right, so let's take a look at the question again. We want EVX as a whole to have a value of 566E7F as a hexadecimal number. All right, so we'll go ahead and start to work on this. And once again, I will split the screen again so that we can look at the question on one and then work on the solution on the other one. Okay. And as we work on the solution, what we want to do is to do it step by step. In other words, we want to find out, what are we going to copy to EVX? Okay. What is the order? What is the byte sequence that we have to copy to EVX? But in this case, we only want to deal with the most significant 2 bytes first. Okay. Why am I more interested in the most significant 2 bytes in this case? How many chances do I have to set or change the most significant 2 bytes of EVX? I got 1 shot to do it. Okay. The least significant bytes, we kind of have a few. We have 1 more chance to change one of them. But the most significant 2 bytes, I only got 1 chance, which is this instruction here. So let me turn on the line numbers so that we can refer to line numbers as we talk about it. Okay. Instead of making this sentence a little bit too long and wrapped around, I'll just say the byte sequence that we have to copy to EVX, and the most significant 2 bytes would be what? The question is asking this. This is the content in EVX after the whole thing is done. So can someone tell me the byte sequence of the most significant 2 bytes? To be 5600. Okay, because it is little endian, so the 56 being the least significant byte of the most significant 16 bits needs to go first. The 00 is basically the 00 before the 56 is basically just leading zeros to pad it to an 8-digit hexadecimal number. Okay, So now that we know what we are looking for, let's go back and look at how the memory content is initialized and see if we can find it. Okay. So we want to look at the byte sequence on this line here. The byte sequence in this line is 7F, 0x7F, 0xe6, 0x56, and 0x00. Ah, okay, that's easy. And then, well, since we're here, might as well just look at the next one, which is just 5 itself. The one before, it would be some 4 bytes. So the 4 bytes, I'll just kind of use this notation here to indicate that we have 4 bytes, but we don't know what they are. In other words, we cannot rely on those 4 bytes as the final destination or to specify the final content. Okay. So we have just, yep.
Would those 4 bytes be different depending upon what computer you're on, basically? Or what?
Yeah, it depends on a lot of factors, how your kernel wants to load your program and stuff like that. So those 4 bytes, and on paper, we don't really know what they are going to be anyway.
Yeah.
Because without GDB, you really don't know what L1 is going to be.
Mm-hmm.
So we cannot rely on the values of those 4 bytes.
Okay.
Okay. All right, so we have just figured out, in this case pretty easily, where we're supposed to copy from. So that means I have already specified, I know, okay, in this case, I know this has a effective address of what? Well, I cannot remember the labels here. So relative to L1, where is the first byte corresponding to the least significant byte of the .int on line 20? L1 plus 4. It's L1 plus 4 because L1 is actually the address of the first byte of this .int, and this is the second .int, so that's why it's off by 4 bytes. Okay? All right. So now that we know that has an effective address of L1 plus 4. Okay. But that's actually very helpful because that means question mark plus EAX plus EBX has to be L1 plus 4. Okay. Next, we will take a look at EAX here because EAX is already initialized, which is a very useful thing. It's initialized by this instruction. Can someone remind me again what is the first operand? What kind of operand is it? I know it's well, first of all, is it a memory operand or is it a register operand or is it an immediate operand? It's a memory operand, but within the memory operand family, what kind is it? It's a direct operand. All right, very good. So, so do I know the value of EAX after this instruction? What is the question mark?
Unknown.
Unknown. Well, is it really unknown, or we just don't know the exact value, but we know what it is? Let's take a look.
Depends on what L1 is.
Okay, let's take a look at the first part of the program here. L1 is right here. In other words, L1 as a label is the address of the first byte of L1 minus 4. So that means when you move L1, you're moving L1 minus 4 as the value into EAX. Okay, are we doing okay so far with this? So EAX actually equals to L1 minus 4 after this. Is that okay?
Yeah.
We saw something similar to this in our, our other homework assignment. Is that okay? The 4 bytes at L1 in memory turns out to be the address of something else. That's basically what it is. Okay? Now how is this helpful to us? Well, it's helpful to me because now I know the effective address is question mark plus L1 minus 4 plus whatever the value of EBX is. I have just solved one unknown in this equation here. So the next question is, how can I load, what should I put into EBX in this instruction so that this will make sense?
max 4 bytes. The max 4 bytes.
Okay, well, let's take a look at this equation again. The equation itself is I want the whole thing to become L1 plus 4, right? I want this entire expression to be L1 plus 4. We already know EAX is L1 minus 4. Can I simplify this equation? Well, L1 can be removed from both sides, so we have 4 on one side. Oh, I need it. Place it with a comment here. So L1 is taken out of the whole equation, so now we only have question mark minus 4 plus EBX is that mess here. Okay? So what is that telling you? Do you think EBX is a value that involves L1 itself, or do you think EAX is EBX? Do you think EBX is just a fairly simple value, some kind of integer value? Probably something simple. Okay, I don't think we need anything that's complicated in EBX. In other words, if you want to do this take it one more step, you can say EBX is basically 8 minus the question mark. Okay, so it has to be, it's probably some kind of really small value. All right, so the next question is, where do I get that small value into EBX? Well, as it turns out, EBX is fairly easy to deal with because you have line 28 to allow you to specify anything into the 32-bit of EBX. Okay, why don't I change that to a 0? And then just use this line to control the last part of it. Would that make any sense? Remember, we have multiple solutions, but this is the easiest one. Okay, so if I put a 0 into EBX, then it's up to this instruction to determine what actually goes into the register BL, which is the least significant byte of EBX. So I'll just go ahead and propose this solution to that particular instruction. If I do it that way, I might as well just make the entire, the entire thing 0. Where can I find a byte of 0 in the initialized memory portion of this program? Can someone point out to me? Well, I guess it's a little hard to point out. How about this byte here?
L1 plus 8.
That will be L1 plus 7. It's L1 plus 7 because this byte is L1. It's at location L1, L1 plus 1, L1 plus 2, L1 plus 3, plus 4, plus 5, plus 6. This is plus 7. Okay. But I cannot really just specify L1 plus 7 because I can only specify the question mark here. So how should I specify the question mark? Now that I know that EAX is L1 minus 4.
Should be moved.
Let's see, we want L1 plus 7, right? And we know EAX is L1 minus 4. So we are off by 11 bytes. So if I just make this 11 in using EAX as a base register, that should do it.
Okay, should that be move B instead of move L1?
That should be move B. I'm sorry, I cannot copy. Question? That was a hand.
Yeah, can you just repeat what you just said?
So let me just write down the rationale here, okay? Okay, we want this to get this byte from location L1 plus 7. Is that okay?
Yeah.
We know this is L1 plus 7 because this one is at L1, so this one is at L1 plus 7. Okay. We already know EAX equals to L1 minus 4. Is that okay?
Yeah.
That's coming from the first line of initialization with our EAX register. Okay. The effective address of an offset in a base register is really just the question mark unknown value plus the value of EAX. And we want that to be L1 plus 7. Is that okay? But at the same time, we also know what is EAX at this point. We know that EAX is L1 minus 4 already. So when you simplify the equation, you can cancel out the L1, add 4 to both sides, then we end up with question mark equals 11. So that's why I choose 11 as my displacement on top of the base register. Okay? All right. Yep. Go ahead.
Which one was?
Sorry?
Me? Okay.
Yeah.
This L1 minus 4, like, I'm not really seeing how it's plus 11. Like, I'm not getting what's going on with this L1 thing because it's,
Okay.
you start out, L1 is the memory location that begins at the execution before into L1 minus 4, right?
At location L1 in memory,
Right.
there are 4 bytes.
It's not before.
When you
it's
look at the
after.
4 bytes together as a 32-bit number, that turns out to be the value L1 minus 4, which is the address of this byte here. Okay? Is that part okay?
I didn't get that.
Okay, this is,
Yeah.
look at this as a pointer. And the value of the pointer is the address of somebody else. Okay? So at this, okay, these 4 memory locations turns out to be the address of this location, which is not what we're interested in. But nonetheless, it is a fixed point in memory, and we can use it to calculate, to get to the location that we want to get to.
Okay.
Is that okay?
Might have to ask you more about it later.
Okay. Yeah, this is all conceptual. You know, these are all concept questions. They're not empirical. In other words, you know, we should be able to solve all of these problems without GDB, because you know, because I give you the byte order. I mean, the content of EBX in hexadecimal already. So that means you don't have to do any base conversion. It's already done. Okay. Yep.
So that's L1 minus 4, but then you have dot word right before it. So what's confusing me is why do you count each
Oh, my
word?
calculation is wrong.
Okay.
You know, the address, this address L1 minus 4 turns out to be the address of this byte.
Okay, okay.
Yeah. I forgot it. There's another dot word next to it. There are 2 items on the dot word
Right,
one.
okay.
Okay. My bad.
And then the other thing in the beginning, which we've kind of gone away from because we put 0 on line 29, but you said
On line 29.
you said initially that we wanted L1 plus 4
L1 plus 4.
when we were talking about EBX. But that's 7F, and I thought initially we wanted 5600, so that would be L1 plus
Well,
6. And
oh
L1
yes,
plus
yeah.
7.
We want these 2 to become the most significant bytes of EBX. But you cannot just copy the most significant. You cannot just copy
Oh, right,
the most
right.
significant 16 bits. So when you're copying, you're always copying
4.
32 bits, and as a result, you
Okay.
have to start copying from this location, which is L1 plus 4.
Right, okay, thanks.
Mhm. Okay, are we still doing okay so far? Okay. So now, you know, we have to specify the last one here. Now, by the time we get to the last one, now let me just kind of comment here and say, you know, after this, EBX is 0. Okay? We try very hard to make it 0. So that we can do the calculation very easily. Okay, so that means by the time we get here, we can now, you know, do the question. We can present the question. We can continue with the question with one fewer unknown because EBX is 0. So now we have just 8 minus question mark is 0. So what do you think question mark should be?
8.
It's just 8.
Depends what number system you're in.
All right. So I have just worked out this instruction, right? So all I'm going to do here is to copy and paste it and just say, if I turn this into 8, that should work. Now there's one more instruction here. This instruction is move B indirect EAX to BH. Okay, but what exactly is EAX at this point? We never changed EAX after the first initialization. So EAX still has L1 minus 4. Okay, but you don't have a choice here. The question is it still going to do the right thing? What do you think?
Yes.
I hope so.
It's still going to do the right thing because L1 minus 4 turns out to be this byte, and we are copying this byte to, is it this byte?
L1 minus 4.
We're copying it to here to the second byte, the second least significant byte of EBX. So that won't work.
No, that's right.
And we're doing it
That's
all
what
plus
you want
one.
in the instructions. It says 60.
Yeah, 660. Yeah.
Oh, okay.
Yeah.
Okay, so we do have to change that byte to 6E. I didn't read my own instructions well. I would have flunked my own test. But for very, very bad reasons. Okay, the question is up here. Okay, the question says I want to end up with 6E. Okay, so that's why 6E is actually, that really is the byte that I want to copy. So that will finish up the whole operation. Okay. But by the time we get to that instruction, we really have no degrees of freedom anyway. Because we have already used up all the question marks, to get everything else done.
What about BL though?
BL? Oh, BL is already done, right? I mean, BL is supposed to have a 7F, and the 7F is already in the original 4 bytes that I'm copying into EBX. So that one is there, is already there to begin with, and
So we're just altering.
this is the only byte that I have to alter to get it to the correct number at the end. Right. So this is a good exercise. I think it's I think it's a little bit simpler than the homework assignment in some ways. Because there's no base conversion; it's already done for you. You just have to do the calculations. Just solve the unknowns. And for the most part, if you try to make one of those registers 0, it really makes everything else easier to compute. In this case, EAX is also fixed, which is a great help too, because we already know in this particular equation on line 40, you already know that EAX has a value of L1 minus 4 at that time, and that really helps to simplify everything because you know that you have control over the question mark. Question mark can be anything that you want. So now the only thing that you have to kind of make sure that you make it reasonable is EBX. You just have to make sure EBX becomes a fixed value so that you can compute the question mark as a result. Okay, are we doing okay so far with this one? All right. I'm just going to check the recorder because I think this is a pretty important one to record. All right. Next one is question number 3. And here's question number 3. Specify a single value to replace the question mark so that the sign, overflow, and C flags are all set when the program stops at checkpoint. That's part 1 of the homework assignment. Part 2 of the homework assignment is to find out the range of values to replace question mark so that these 3 flags are all set. You may express the inclusive boundaries of the range in decimal or hexadecimal representation. Specify the ranges here. In other words, I give you a space to write your answer, so I don't have to look through the entire piece of paper to look for your answer. All right, so that's question number 3. We want the sign, overflow, and the carry flags to be all setting. And your only degree of freedom is to change that question mark. So let's deal with first part. Okay, the first part first. Part 1 is just saying, find a single value to make this happen. And then part 2 says, give me the entire range of values that will make this happen. So obviously part 1 is a whole lot easier because you can just kind of intuitively say, oh, I think this value is going to work, and then try it out on paper. If it works out, you get partial credit for part 1 already. Part 2 is a little bit harder because you have to find out the extreme ends of that range of numbers, and then you really have to kind of think about how the flags interact in that case. Okay, so to answer the question, you basically have to figure out, okay, what am I subtracting from what? Okay, what are the bit patterns? I would not even look at negative 32. I would not even look at negative 34 itself. I would look at the bit pattern representing negative 34. Okay, because the processor really doesn't deal with positive or negative numbers in decimal. It deals with bits. So it is best if you just look at things from the perspective of the processor. So the first thing I would do is to convert negative 34 into its binary representation. Okay, its binary representation is the 2's complement of 34. In this case, 34 is a decimal number. Yep.
Remove byte and compare byte. Is that possible with EAX?
Yeah, you caught me. This is A, L, and AL. Okay. The assembler will give you a warning, but it will still do the right thing, because the value, the negative 34 value, is well within the range of a byte.
But that would change the boundary of overall.
That will change the boundary a whole lot, yes. All right, but assuming this is what the question is asking, we have to find the 2's complement of 34 as an 8-bit number. As an 8-bit number, we have a 2, and then we have a 32, which is that. And then we can pad the rest of it with zeros. Okay, let me double check and make sure that makes sense. This is 1, 2, 4, 8.
16,
Oh, that's
so
16. So I'm off by 1. There we go. Okay, so 1, 2, 4, 8, 16, 32, and I need one more 0. So now we have 8 bits. Are we doing okay so far? How I did the base conversion? Okay. You can bring your calculator. You can bring a calculator that can help you deal with a base conversion. So that part should not bother you much. And 2's complement is really a bitwise NOT. The bitwise NOT operator in C is the tilde symbol. Okay, that's the bitwise NOT in C. And you have to add 1 to it as a result. So the bitwise NOT is just flipping all the zeros into 1s and all the 1s into zeros. So now we have 1, 1, 0, 1, 1, 1, 0, 1. Just add 1 to it, and the end result in binary is that. Are we doing okay with the base conversion and also 2's complement? So now that we know this is the number that we are subtracting, this is the we are subtracting this from from AL in this case. So our subtraction is really AL minus this bit pattern, 1101, 1110, and I want the result to end up like this. I want the borrow to be set, because the borrow is our carry flag. I also want the sign flag to be set, right? Because I want the sign, overflow, and carry flag to be set all at once. So can anyone kind of guess what is this 1 bit here at the cursor position? Okay. It has to be a 1 or a 0. Okay, when the overflow flag is set after a compare instruction. Oh, but I did say that I wouldn't ask you anything about compare, but let's do this anyway. It's going to be helpful, right? Okay. But in a compare instruction, which is a subtraction instruction, how can I make the sign of the result not make any sense? We are subtracting a negative value from something and ending up with a negative value.
Positive.
Positive, that's right. So I know that I need this to be a 0. Okay. Now this is already really helpful because I already know what kind of, I know something about this bit pattern already. And I also know that the borrow flag is going to be set anyway, because 0 minus 1 is 1 with a borrow. So I don't have to worry about the carry flag anymore. This really sets up, and say that now I just need to specify the rest of this bit pattern. The 7 bits next to the 0, that's the only part I have to specify to guarantee the result that I'm seeing here. Okay? Is that making any sense? Okay. All right. Now you can also look at this from another perspective. The other perspective to look at this is the sign of the result makes no sense. In other words, I want it to be x minus negative 32 to be some kind of result. So I want this result sign to make no sense. Now, what does that really mean when you're dealing with 8-bit calculation? It means the result cannot be stored in a 8-bit number. Okay? Okay, so let's write that down too. This means the value of x minus negative 32 cannot be represented by an 8-bit signed number. Is that making any sense? Because that's the only time where the overflow flag will be set, is when the sign does not make any sense. But the only time you get this case is when the result cannot be stored in an 8-bit number. It requires more bits to represent. Okay, x minus negative 32 is the same as x plus 32. Okay, so, yep.
34 and with negative
34. Okay, I keep.
Before you get too far.
All right. Okay. This is the same as x plus 34. And we want x plus 34 to be a value that cannot be represented by an 8-bit signed number. So now the question now is, do you think I want this sum to be a positive number or a negative number?
Positive.
Has to be positive, okay? The largest value, or the most positive value that I can represent using signed chart is what? 127, very good. So that means I want x plus 34 to be greater than 127. You can solve an inequality by subtracting the same number from both sides. So that means x has to be greater than 127 minus 34. I need a calculator for that.
Where'd you get the 127? How did you get the 127? How did you get
The most positive value I can represent using a signed character is 127. Because
8-bit 128.
Because it's a 0 followed by 7 ones. And that turns out to be 127.
the first number you found, the 0 that subtraction. So then that's
You kind of have to remember the number wheel. Remember the number wheel that we talked about once? I divide it into 1/2. 1/2 of it will represent non-negative values, including 0 itself, and the other side will represent negative values. Do you guys still remember that? The one side that is non-negative starts with 0, but I want the wheel to be using 1/2 to represent non-negative and 1/2 to represent negative values. So that means each side can only have 128 values for an 8-bit number. But because 0 is taking up one slot already, so that means the most positive value is going to be only going to be 127. 128 is out of the range already. So that's that's why we have 127 as the extreme end of the positive side. Yep.
0 and 7 ones, or 7 ones and 0?
0 as the most significant bit, and then everything else being ones. So it's 0, 1, 1, 1, 1, 1, 1, 1 is the bit pattern of the most positive value you can represent when interpreted signed. Okay. So I have just answered both parts of the question, because if x is greater than 93, it will solve the problem. There's only one thing left, because x actually has a range. Even though x can be greater than 93, x cannot be x has to be less than or equal to some value. 127 has to be greater than or equal to x, and x has to be greater than 93. Why do I put this constraint here? 127 is as large as x can go. Exactly. Because if I put it, if x is quote unquote 128, in this calculation, it will be representing negative 128, and the flag combination would not be the same anymore. So that's why 127 is the extreme, because you can actually see that limitation as well when you look at the subtraction. It's because of this 0 here. We can make everything else ones, but the most significant bit has to be a 0. So that puts a limit of how big x can be. Are we doing okay so far? So I have just answered both parts of the question, because x, for the first part, it's easy. 127 would do it. But for the second part, the range is going to be from 94 all the way to 127 inclusively. So if I were to go back and write down the answer, I would go back to here. Just one boundary would be 127. That's the easy boundary to find. And then the other side of the boundary is 94. Yep, go ahead. 93? Oh, 90. It's an inclusive range, so it's 94. Yeah, because I asked the boundaries to be inclusive. But obviously, if you write 93, I'm not gonna take out all the points. I mean, I think you know how to get to the answer, and you just forgot about the greater than versus the greater than or equal to. All right, that's our third question. Shall we move on? I'm hoping the documentation that I put into the document is somewhat helpful, so that you can actually read that as a reminder of how we came up with the answer. So Q4A is here. Question number 4 is, in the area indicated, insert your own code to multiply the value in EAX by 69 and store the product in EBX. You are allowed to use up to 1 move L instruction and 9 add L instructions. There's no operand restrictions. When I test your code, I will reinitialize EAX to a different value. 23 is just an example, so you have a value to test your code with. You do not need to preserve the value of EAX in this process. 2 hints, okay? Now these hints are really big. The first hint is to look at the following instruction doubles the value of AL. Is that any question about this line here? This is doubling the value of AL? No questions? A bigger hint, look at the values using the binary representation. Now, I didn't quite say which one, 23 or the other number, but remember, I will change the initialization of EAX to test your code, so that kind of implies that you probably should not be looking at 23 in binary. You should be looking at the other number, which is 69 in binary. Okay, so this kind of relates to something that we talked about already, how to do multiplication in binary. So the question is, how do you specify your code here? Any suggestions of how to proceed? Let's do it by hand first. I have x, which is our so-called 23. I wanted to multiply that by 69. Okay, so I can end up with 69x. Is that okay? That's my problem. Except in this case, I can only use the the instructions that we have talked about to deal with it. And we have not talked about the multiplication instruction. So the question is, can we multiply an unknown by a fixed number, a constant, using just add L and move L instructions,
Easy, yeah.
and not using 69 add Ls? That would be kind of obvious. That's why I have a restriction of only up to 9 instructions, not 69.
Well, the thing is, we just double it.
We have to double it each time, so what we need to do is to rewrite 69 in a certain way, okay? So the first thing we have to do is to look at 69 in a different way. So we say 69 is 1 plus, okay, let's do it from the other side. 64 plus 4 plus 1, okay? Why do I break it up into 64 plus 4 plus 1? Are those just kind of random numbers? No, they're powers of 2. Okay. So that means 69x is 64x plus 4x plus x. Right? Now how is that going to help me? What if I use one register to keep track of 1x, 2x, 4x, 8x, 16x, and so on, and I use the other register as a summation register so that I would just add up the right ones at the right time? Are we doing okay so far with that? Okay. So that means I would use, okay, according to the question, I want the product to be in EBX. So I can use EBX as the summation register too. Okay, seems to make sense. So if I use it as a summation register, I will use my one move out instruction to initialize my product. Okay? And since it doesn't say anything about EAX itself, you can destroy the value of EAX. So the first thing we'll do is we'll say, well, actually we can make this even easier. The first thing is just to copy it, okay? So that then we'll add L EAX to EAX, and the comment is, EAX is now 2x. Do we care about 2x? No. What about 4x?
Maybe, but still.
Oh, we need 4x. So if we need 4x, we'll just say, okay, we'll add EAX to EBX at this point. Next one up is 8x. Do we need 8x?
No.
Yeah. How about 16x?
No.
Yeah. Do it again, it becomes 32x. No. We're getting there. 64x, we like that one. So we'll say add 64x to the summation register, and we're done. I think I did it with fewer instructions than this.
8.
Yeah.
Did we miss X? Didn't we miss X to the inner EBX?
Nope.
I see.
We did not miss because
Yeah, it's probably because you went ahead and added EAX and instead of initialized to 0. If you
Right.
initialize 0, you'd need none of it.
right. Well, initializing it to 0 is the more quote-unquote general way to do it. Because you can always find out which one is the first one, and then you just don't initialize to 0. But initializing it to 0 means you can turn it into a loop later on.
Okay.
So are we doing okay with this one? That's it. We finished everything with 10 minutes to spare. I think we can add like another bonus question to the whole mix.
Does that mean there's going to be a extra credit question?
I don't think anyone will need extra credit question or want extra credit questions. Yep, go ahead.
So, these are the types of questions that we're seeing in the test?
This was the exact question. These were the questions of last year's exam.
So it'll be like, we'll come and take the test, we'll have 3 questions, it'll be the same kind of questions.
4 questions.
But different numbers or whatnot?
It'll be there will be 4 questions, and obviously they won't be the same, okay?
Right.
But they will. But this illustrates, what kind of understanding I'm expecting, you guys to have. So basically, you have to understand not only the individual operands, the direct, indirect, based, scale, indexed, and so on, and not only just the add instruction, but also how to apply those things and reconnect them to implement something that we may or may not have seen in the class.
So how far will you deviate from these examples?
I do not know yet. I need a little time machine to figure that part out.
Sky's the limit, creativity.
How do you slay the dragon with EBX?
Well, you use immediate operators, of course.
But I don't know yet. I really do not know because I have not come up with the questions yet for next week's exam.
Is it going to be written or in the lab?
It's going to be written, so it will be the same kind of format. I will give you the code, I give you the instruction, I give you some empty space, so they can specify your results.
Is this next Thursday?
This is next Thursday, right?
That was my question.
Okay.
The homework is due that day also.
Sorry?
The homework's due on that day also?
No, the homework is due on Tuesday.
Okay.
So you guys will have the solution to the homework assignment before the test, which definitely helps. And you will not have compared instructions because I said that you will not have compared instructions. And it's being recorded, so I cannot go back to my own words unless I go back and change the recording.
I'm making a copy.
Beep that out, right? You will not have beep in your examination. We're not done yet. Let's go ahead.
So now that the homework is due Tuesday, will it be staggered and all the homework will be due on Tuesday until the end of the semester?
I don't think that this is a shift operation, so it doesn't change all the other bits. Okay, so we still have 5 minutes left. Let's go ahead and continue our discussion with conditional branches. Okay.
There we go.
Did you guys read the notes as I suggested last time?
Yeah, of course.
You know what this reminds me is my own piano lessons when I was a kid. On Saturday, it's time to go, take my piano lesson, and then my piano lesson, who turned out to be a French sister, as in the Catholic Church, sister, who was teaching pianos in Hong Kong. So she speaks Cantonese with a French accent. And she was an old lady too. She was a very old lady. She's really good in a way, but she has a very short temper. So when she asked, did you practice? It's a really tough question to answer. Because if I answered yes, then she will have the expectation, and then when I cannot play the pieces, you can expect, like whack, I actually broke her pen once because of that. I should say that she broke her own pen when she hit my finger with her pen. But I'm lucky to be a guy because I have short hair. With girls, which is the majority of her students, she would actually tear the hair. She would actually grab the hair and shake the head and go like, "You didn't practice." Yeah, not quite the image that you normally have when you think about sisters, like in The Sound of Music, right?
I'd like to see that. If they don't read, you just grab their hair.
That's the exact image I had, actually.
That was just spoiled. I guess Austrian sisters are different. All right. So basically, we are done with jump instructions, and now we are on to control structures. And there are 2 of these. One is an older version, and one is a newer version. Okay. And I think this is the newer version. Yep, this is the newer version. The newer version is better, and that's why there's a newer version, because the other version is a little bit more cumbersome. But it still has the same content, basically the same content. It's just a little bit different, explained differently. All right. So what this chapter will do is it will explain to you how quote unquote compilers work, end quote. Okay. Because what we are doing is we are looking at common high-level language constructs, and then we think about given all the pieces that we have introduced so far, which is not a whole lot, we got the move instruction, the add instruction, subtract instruction, and the compare instruction, unconditional branch, and conditional branches. That's all that we have up to this point. How do we use these really simple pieces to implement all of these things that we are going to talk about? So I'm just going to skim through the notes a little bit in the next 2.5 minutes and point out the really important parts. Of course, you guys have to read the rest, right? I mean, you have to. All right, conditional statements. The first thing that when you look at these notes here, whether it's conditional statements or loops, pre-checking or post-checking, it's introduced in exactly the same format. The first thing I'll do is to turn something that is structured, and this is the perfect kind of code, and turn it into something that is really ugly. But that's the same thing in C. Okay, so let's take a look at this particular example here. This is regular C code. Okay, BLK1 and BLK2 are basically a block of code, block 1 and block 2 basically. So it can be one statement, can be multiple statements. It doesn't matter because I use the curly braces to turn it into one single compound statement. So I start with something that looks really nice like this, that your CISP 400 professor will definitely accept and say, yeah, this is the kind of code I want you to turn in. And I turn it into something that has the tabooed word go to. Okay? But this is still straight C. This is still completely C language. Okay? There's no assembly language here. But does it represent the same logic? That's the question. That's the first question. Does it represent the same logic? If not C, if whatever C is, C can be a long expression like this, can be a very simple expression like this. I don't care what it is. I just negate it. If the condition is false, I go to label L1. Where's L1? L1 is right before block 2. Is that the proper behavior for the else part? Well, when the condition is false, you should go to the else, else branch. And after the else branch is done, I'm done. The L2 is just a label for the end here. It doesn't really, I don't specify what is after L2, which is the next statement. What if the condition itself is true? If the condition itself is true, then okay. What if condition is false? What if C is false, I should say? Then not C is true, then we go. What if C is true? Not C is false, and we do not go. So the go to would not happen. If the go to doesn't happen, then what is the next thing to do?
Block 1.
Block 1. After we are done with block 1, we have a go to L2. L2 is down here. So that means after block 1 is done, we do not continue with block 2. Instead, we just go all the way to the end. Is that the same behavior as the proper C code up there, the structured C code? Yes. Okay, so what I have done is to quote unquote destructure regular C code. We start with something that is structured, we turn it into something that is unstructured. There's only one reason to do it. The reason why we are doing it is because this will eventually be replaced by a conditional branch instruction. Does that kind of resemble a conditional branch instruction to you? Sometimes we branch to a certain label, and other times we do not. Okay. And what about this go to here? Does it resemble a particular instruction that we have talked about? The unconditional branch instruction is our go to. So this is the first step. Now, if there's no else, then we start with something like this, and it gets translated to this. Okay. You can also use this template and just remove block 2. In other words, you have an empty block here. It will still behave the same way, but you just have some unnecessary go-tos and some unnecessary labels. It still behaves the same way. So if you read the next 2 constructs, basically the same thing. One to deal with the while loop, and one to deal with the do while loop. Now after this, I'm just going to give you a little roadmap of what we are going to talk about next. Is what if we have logical operators? Because so far with this kind of stuff here, to translate this into a conditional branch instruction, C has to be a very simple comparison. Does x equal to y? Is x greater than y? Is y less than 0? And so on and so forth. We can deal with those pretty easily because we can have a compare instruction followed by a JL, JNL, JE, JZ, and so on and so forth. But what if the condition itself has a conjunction in it? What if it is X is greater than Y and Y is greater than Z? We don't really have the tools to do it yet. Well, I haven't demonstrated how to do it. We actually have the instructions already of how to deal with it. So that's basically what the next, if you look at section 4, that's what it is. If you see a not, you turn it into something that does not have a negation. If you see a disjunction, you turn it into something that is more complicated, it's longer, but there's no disjunction anymore. So we are reducing the operators. We're basically saying we will do a trade-off here. Instead of using logical operators, we'll use more statements to do exactly the same thing. And the conjunction is the stranger one. If you have a conjunction, we'll turn it into something like this. But every step along the way, we are making it simpler. So hopefully at some point, the condition is going to be just a simple comparison. Are we doing okay so far with this? So this is just a roadmap. We will take a look at these examples in details after the exam, but I just want you guys to kind of know what is coming and actually study it a little bit. And then after that, we have the actual translation, dealing with a comparison. So in general, if you see, X, R, Y, X is a value, R is a relationship, and Y is another value, you turn it into something like this. The R goes here, X becomes the second operand, Y becomes the first operand, and the L1 is just this L1 here. But when we cover this, you will see that we are just using all these mechanical steps so that we can gradually decompose a structured program into assembly language. But we are doing that without using our gut feeling, without using, well, I think this is going to do it. We're turning into a very mechanical method, do it step by step. Okay? So that's what we are going to do, probably sometime next week. After this, we'll deal with subroutines, because these are things that are useful, but at some point we have to deal with subroutines because we don't want to deal with a certain function that is 500 lines long. So we want to be able to break it up into subroutines. But when we talk about subroutines, then we'll also talk about parameters and also returning values and stuff like that. So it's just a preview of what is coming. But for now, study for the exam. Make sure you know everything really, really well and know how to apply them.
We can bring as many notes as we want.
Oh yes, the exam is open book, open notes, but no computers during the test. Okay, so if you store all your notes on the computer, print them out, and bring the paper.
So we can do like sample code that works. Just saying, just the sky's the limit for everything.
As long as it is paper-based, yes, you can bring anything you want. You can bring my own notes here. If you think one of the screenshots is going to be helpful, take a screenshot, print it out. There's no limitation.
That makes it a lot easier.
Well, when this class was not this big, when we only have like 25 students in the class, we would take the test in the lab, and I would just say, use any resources. As long as it is not live communication during the test, use Google, use Wikipedia, use anything you can find.
Oh, I will.
Makes sense.
Did you record the last lecture?
The last lecture was recorded, but the file was corrupted.
Oh.
So there was nothing. I'm sorry.
Because I missed the last lecture.
You might want to talk to one of your fellow classmates and see, who took notes.
Hey guys,
Yeah.
I'll look.
I'll figure it out. I'll just go through the notes.
Yeah.
I guess.
Yeah.
Pretty much just went over.
We talked about conditional branches. Conditional branches, how do you use the flags in conditional branch instruction? So you just have to read that part. It's all in the notes already. If you read the notes and understand the notes and do some experiments on your own to kind of just try it out, you would probably get the same thing. It's just that the recording didn't quite work last time. And that's why I was a little anxious, at the beginning of this class, thinking, well, it may or may not work.